IES Technology Engineering Tutorial. Insulated Gate Bipolar Transistor. What is an IGBT? The Insulated Gate Bipolar Transistor, IGBT, is a power switching transistor that combines the voltage control advantages of a MOSFET with the high current and voltage handling capabilities of a BJT. It takes the high input impedance and high switching speeds of a MOSFET together with the low saturation voltage of a bipolar transistor, making it ideal for power supply and motor control circuits. High input impedance. From MOSFET technology. Low saturation voltage. From bipolar transistor. Zero gate drive current. Voltage controlled operation. The IGBT as a solid-state switch. The IGBT combines the insulated gate technology of the MOSFET with the high current and voltage handling output characteristics of a conventional bipolar transistor. The result is a device that behaves like a power BJT but is controlled like a MOSFET. IGBT operating principle. The IGBT has the output switching and conduction characteristics of a bipolar transistor but is voltage controlled like a MOSFET. IGBT construction principle. In effect, the IGBT is an FET integrated with a bipolar transistor in a form of Darlington-type configuration. IGBT construction. The IGBT is a three-terminal transconductance device combining an insulated gate N-channel MOSFET input with a PNP bipolar transistor output in a Darlington configuration. Gate, G. The voltage-controlled input terminal, isolated from the main current path. Emitter, E. Output terminal forming the conductance path with the collector. Collector, C. Output terminal, current flows from collector to emitter when the device is on. Switching characteristics. Turn on. Apply small positive voltage across gate emitter. Conducting. Very low on-state resistance RON, high current capability. Turn off. Gate signal set to 0 or slightly negative to block conduction. Unidirectional, current switches only from collector to emitter. Lower RON, much lower on-state resistance than equivalent MOSFET. Voltage controlled, no continuous base/gate current required. Forward blocking, identical operation to a power MOSFET when off. IGBT versus MOSFET versus bipolar transistor. The IGBT combines the best attributes of both the BJT and MOSFET, achieving voltage ratings and current ratings that neither device can match individually. Result: greater power gain, higher voltage operation, and lower input losses than either device alone. Key advantages of the IGBT. 1. High voltage capability. Handles voltages greater than 1 kV, far exceeding equivalent BJT or MOSFET devices in demanding power applications. 2. Low on-state resistance. Much lower RON than an equivalent MOSFET, reducing I2 or conduction losses for a given switching current. 3. Simple gate drive. Voltage-controlled gate requires virtually zero gate drive current, making it far simpler to control than a standard BJT. IGBT applications. IGBTs are commonly used wherever the demands of solid-state switching are not fully met by either a power BJT or a power MOSFET, spanning renewable energy, industrial drives, and high-frequency power conversion. 1. Inverters and converters. Solar power DC, AC inverters and frequency converters operating in the hundreds of kilohertz range. 2. Motor and speed control. Pulse width modulated, PWM. Variable speed drives and switch mode power supplies for electric vehicles and industrial systems. 3. High voltage power supplies. Driving inductive loads such as coil windings, electromagnets, and DC motors with high voltage at moderate switching frequencies. Operating the IGBT. Turning the IGBT on and off is straightforward due to its isolated gate structure, making it far simpler to drive than a bipolar transistor. Goal: leverage voltage control for efficient, reliable power switching. Apply positive VGE. Small positive gate emitter voltage turns device on. Current conducts. Collector-emitter path conducts with very low on-state loss. 0 or negative VGE. Gate signal removed or reversed to turn device off. The IGBT can also be operated in its linear active region for power amplifier applications, offering flexibility beyond simple switching use cases. IGBT Summary 1. Ideal applications. PWM, motor drives, solar inverters. Moderate speed, high voltage switching. 2. Superior performance. Voltage 1 kV, current 500 amp. Outperforms BJT and MOSFET combined. 3. Simple drive. 0 gate drive current. Voltage controlled, easy to implement. 4. Hybrid design. MOSFET plus BJT in one device. Best of both transistor technologies.